Hello, everybody. So we're going to be doing a review of Unit 3 today on the chemical reactions. So this unit is the crux of what chemistry is really about. That's why I like it so much. All right, so let me show you the assignments that we had for this. All right, everyone quiet, please. The assignments that we had, first we discussed the driving forces for reactions to occur, and then we practiced writing them, so you used arrows and you had correct formulas. Then we did a lab, which I would grade separately, all right, on precipitate or not. That is a double displacement reaction. Then we did a second thing on balancing reactions, because we had done in this class, remember, we had done some balancing. Then on that one day where I just wrote out reactions for you. All right, then we balanced single replacements again. Then we practiced balancing synthesis, where two elements combine. Then we practiced decomposition, which was just last week. Then we practiced combustion reactions that produce CO2 and H2O. And then we saw one that didn't get enough oxygen that produced carbon monoxide yesterday. And then we had some practice identifying reactions and balancing equations. All right, so these are the assignments that we did to support these objectives over here. So this unit was about 5 kinds of chemical reactions. These are the most common kinds. So previously, do you remember we had done 2 labs on single replacement reactions? One of them was metals plus acids, and you tried to see who was the most reactive. You were so successful that you were able to create the correct reactivities of metals. Then we did one, since you were so hot on that, is we did metals plus other metal ionic compounds based on their location on that reactivity list of metals. It's called the reactivity series. Then you did pretty well on that as well. Those were 2 kinds of single replacement, because a metal was pushing a hydrogen out in acids, or a metal was pushing another metal out. So only one thing was being pushed out. So it's called single replacement. Then we experimented with precipitations in the double displacement reactions. Secondly, we just discussed neutralization reactions in which an acid with H pluses in solution and a base with OHs in solution combines to form the neutral water molecule. So essentially, something with a very high pH, like a base, combines with something with a very low pH, both of which are too caustic to pour over your hands. And then when you pour them together, you get mostly water, which of course is neutral, right? When we drink water, it doesn't hurt our windpipe, our esophagus, does it? No, that's because it has a neutral pH. Our body is at a neutral pH as well. So pH is a significant pH is a very significant concept, because reactions occur better or not at all at certain pH levels in the body or in nature. All right. So we learned there are driving forces that push a reaction to go until one of the reactants runs out. This is an efficient way for a reaction to produce the desired product, because ideally when you put them together, you hope the reaction will keep going until it runs out. All right. We learned how to write the equations. Oh, wait. You probably think this happens all the time. But no, it doesn't. Some reactions do very little work and then stop. They don't go on any further, even though there's reactants left. So this is very efficient to get your reactions to produce the desired product until they use up one of the reactants. We learned how to write the equations with the correct formula. And you know how we learn to write correct formulas using the charges on ions. In an ionic compound, we also learned how many nonmetals were connected to each other when we did Lewis-Dot formulas. All right. We learned how to balance equation using just coefficients, the big numbers in front of the molecules, in front of the formulas, to get the identical number of each kind of atom. On the reactant side is on the product side. That's called some sort of conservation. What kind of conservation is this? If we're counting atoms to make sure we have the same kind and number on both sides of the equation, this must be conservation of atoms. It turns out, though, that we can go more general than that. It means there's conservation of mass in a chemical equation, and there's conservation of matter in general in chemical reactions. All right, but the key idea when we balance is that the easiest way to set up a reaction, set up an equation that shows conservation of atoms is to count atoms. We learned about synthesis and decomposition reactions and how to write and balance these equations. We worked with combustion reactions to see how fuels combine. So we were learning how to recognize fuels like CH4, C4H10, butane, like in butane lighters, methane, like in Bunsen burners. Gasoline is C8H18. This is gasoline, another fuel. All right, so you're learning to recognize hydrocarbon fuels. All right, and then whenever one of these burns, they suck the oxygen right out of the air. All right, which means is you have a fire in your house. It's important to get it out because if the fire continues burning, it keeps sucking oxygen out of the air. And I don't know if we discussed this yesterday, but when there is a house fire, people die from lack of oxygen because it's being used up, right? Then they inhale smoke, but mostly the problem is all the oxygen's used up by the fire, and if they don't get out, then they won't be able to get enough oxygen to stay alive. Okay, so that's a serious problem. So combustion reactions use up oxygen. Then we connected human respiration and plant photosynthesis with combustion reactions, where this is combustion of glucose. Glucose in our cells. And if you're thinking that's what gives you heartburn, my cells are on fire! My cells are on fire! No, the body manages to do this through intricate means so that we keep our temperature at 98.6 while combustion is going on in all of our cells. All right, so this has to be controlled by the body's system of homeostasis to keep our temperature at a constant level. Photosynthesis with combustion reactions, the opposite of combustion. Opposite of combustion, because instead of CO2 and water being the products, CO2 plus water are the reactants. So it's the opposite. And it's good because it uses up CO2 from the air, right? Which we have too much of. That's why we have global warming. It's one of the chief contributors to global warming. Methane is also. Cows, fart. And cow farts create tons of methane in the air. Yeah. I just want to fill you in on all the things. Yeah. So it isn't just CO2 from burning combustion that's the problem. It's also that we're cutting down trees so there's less photosynthesis. And it's also because cows and other animals project a lot of methane gas into the air, which also causes global warming. And then we learned how to identify the 5 different kinds of reactions yesterday when they were in a mixed group. All right? So we have really done a lot. So let's go and look at each one of these then. Starting with April 17th. All right? So, driving forces cause a reaction to continue. This was our first assignment. All right. I gave you examples, the 3 things that commonly cause a reaction to continue. All of them remove a product from solution. Precipitations drop to the bottom out of the solution. Gases leave the solution entirely and go out into the atmosphere, right? And water molecules, when they form, refuse to form ions. They refuse to ionize. And they stay as a water molecule, and that causes the reaction to keep going. All right, so those are 3 typical means. All right, so we did lots of examples here, and I did these examples. All right, but then when we got to the bottom, so you can go and look now, put me half screen and then go to your own screen. So what I did yesterday was go through and look at what are the things that I had not finished because I had left them for you to finish. So this is the driving force April 17th reaction. So I went through and wrote these reactions and balanced them so you could see what I was talking about. All right. Then we went and we did those in class. And then finally, you answered these conclusion questions, but I didn't write them down, did I? Because you were writing them down. So the key idea here is that a driving force keeps the reaction going until one of the reactants runs out. What are the 3 kinds of driving forces? They force the reaction to go. One is a precipitate, one is a gas, and the other is a covalent molecule that will not dissociate. So what are 2 types of double displacement reactions? Well, one's the formation of a precipitate, and the other is formation of water. All right, the formation of water is an acid-base reaction. All right, this is acid-base reaction that forms water. And it's called a neutralization because when you pour an acid and base together, they neutralize the horrible effects of each one. Neutralization is it reduces the horrible effects of an acid you wouldn't pour on your hand. A base you wouldn't pour on your hand, but when you pour them together, it neutralizes the corrosive properties of an acid and base and forms water. And we even bathe in water, right? We drink water. All right. Now, what can you look at to find if one of the products is a precipitate? And remember how good you got it using the solubility chart? We started that a little bit last time when we discussed solubility in the last unit. All right, then we did this lab to precipitate or not using that. All right, so we used the solubility chart then, and you did 4 equations. All right, so I haven't graded these yet. Let's go down to look at what the conclusion questions were. How do we know if a precipitate will form or the container will stay clear? The solubility chart tells us, right? Yeah, we don't have to know it. We just look at the chart. On the last test, you were awfully good at reading the solubility chart. How do we determine its chemical identity if some precipitate forms? We write the formulas and then see, and then look up compound on the solubility chart, right? How do you draw a beaker picture to show what happened? Well, what we ended up doing, oh, I know what's going on here. I'll have to change my ways. All right, how can we show? We just showed that ionic compounds, let me just go back a little, that an ionic compound dissociates into ions. So if we have salt, we know it will form a positive ion and a negative ion because ionic compounds are made of ions, and that's what we're studying. All right? And then the other one, let's just do silver nitrate. Silver is +1, nitrate -1. And then we know in this double wide beaker here, we're going to get some silver combining with chloride and then dropping out of solution. And that's what we're going to see. That is our precipitate. All right. And then the other ones, we had sodium in there, right? All right. Sodium and the nitrate ions just stay in solution because they don't stay together. They just keep on ionizing. So we used these beaker pictures to show the ions, didn't we? We saw that the precipitates looked a little bit different. A lot of them were whitish, right? Some of them look like a cloud. Some of them look like it's snowing. Some of them developed kind of a hazy thing, but then they all precipitated to the bottom of the container, and you could see them gathered up there. All right, I'm going to have to go to 7th hour is for some reason where I put the keys. All right, now balancing reactions. All right, so we did all of these in class, and we did them together. All right, and we balanced them together, and I showed you my way of counting. And then there were some that I left for you to do. So check and see how well you did. So these 5, 6, 7, I simply balanced based on the fact that now I'm counting. See how there's 2 nitrates here? I noticed that, and 2 nitrates here. Oh, then I'm beginning to think this is going to be 1, 1, 1, 1, because there's not a difference in the number of nitrates on either side, and barium has a +2 charge, and so does copper. So that's my indication that probably the coefficients are all 1 in this. On number 6, though, I notice this is +2, the other metal is +1. I know I'm going to have some non-1 coefficients. All right, so I know I'm going to have more of the +1 here. All right, and it turns out then, the way it's balanced, we end up with 2 ionic compounds of silver nitrate and then 2 silver chloride formed. Then this formula has 2 nitrates. This formula has 2 chlorides. So 1, 2, 1, 2. So see, as I said, how you got better. Once we get practice at this, we see things we didn't see before when we were overwhelmed. I'm looking at this and thinking, clearly this is a +3 iron, and this is a +1 metal. So I know I'm likely to have 1s and 3s throughout this, and that just gives me a hint. All right? Now, we did all of these. So the pattern at the bottom of the conclusion questions, was there a pattern in balancing? Yes, it has to do with ionic charges. When metals have +1 and +2, you know they will need to be doubled in compounds. The little guy with +1 will most likely have to be doubled. What's the driving force in neutralization reactions? Well, it's that formation of the water molecule, HOH. It doesn't dissociate. And it's called neutralization because it has a neutral pH. Will that help you remember it? Neutralization reactions create a neutral pH. So it's an acid plus a base. forms a neutral water molecule. What's the driving force to complete the reactions in which solubility is important? Well, that is, the driving force is formation of a precipitant. All right. Now, on the 25th, we were balancing these single replacement reactions, which we looked at before, but we balanced more of them, all right? So we went through and we balanced a lot of them, and we were pretending they were in the little plates that we use, the little cells where we added things together and what they look like. So we practiced balancing those, and then I left 4 to 7 for you to balance. So in number 4, copper and tin have the same charge of +2. So when I look through and count 1, 1, 1, 1, there's already the right number of atoms. Number 5, however, is not. Aluminum has a +3 charge, all right? Cobalt has a +2 charge. So I realize that I'm probably going to have coefficients such that I get 6 chlorines here and 6 chlorines here. All right, and that's what leads to the coefficients of 2, 3, 2, and 3. The bottom one, I noticed that we have Cl2. This is the halogens. If a halogen is more reactive, it can push out the other halogen. Chlorine is more reactive, so it pushes it out. All right, it replaces bromine, and so we end up with KCl, and bromine is out standing by itself. All right, so this is a single replacement because there's only been one. Chlorine replaces bromine. And since potassium, all right, since there's 2 chlorines and 2 bromines, we know we have to have a 2 in front of each of those potassium compounds. So counting atoms works, and we're still counting, but we're getting smarter when we recognize how this is going to work. And then finally, we tried to see if fluorine could push the chlorine out of aluminum fluoride, and fluorine's the most reactive element on the periodic table. So single replacements of the chlorine with fluorine, and we get these 2. All right, and since aluminum has a +3 charge and needs 3 chlorines, we see that the 3s and the 2s are here, so we get 6 chlorines and 6 fluorines on both sides. So there is a method in this madness. All right, let's see. The next kind, these are easier ones. They don't require as much thinking, synthesis reactions. So we already talked about the single replacements, all right, and the double displacements, all right, and how to balance them. Now we're working on the synthesis that element A combines with element B to form a compound. These 2 elements are bonded together. So this is a bonded compound. All right, so let's go down. So in all of these, you were writing, or most of these, you were writing the name of the compound as well. So it's calcium plus oxygen, of course, is going to create a calcium-oxygen compound, right? And the compound would be called calcium, full name, and then ox, first syllable, I-D-E. So this is how we name ionic compounds. So we have to use charges then to get the correct formula for calcium oxide. So you were starting to practice doing that again. That's a skill from last unit. Then we went through and counted, and found out that this will totally depend upon the charges in the things that are combining. All right, so next, copper plus sulfur, calcium oxide plus water. A compound plus a water makes an even bigger compound. A hydrogen plus a nitrogen leads to ammonia. And here I showed you how we figured out how many hydrogens go with ammonia using the electron dot diagram. All right, that we learned with covalent bonding. All right, so we did these, and then I just went ahead and did these for you. All right, so look to see how well you did in these. I'll make them just a little bit smaller. All right, so you can see multiple ones at a time. Then I'll make them bigger in case you want to see one. All right, so then you had to do 8 and 9 all by yourself and create the name. So did you call it aluminum bromide, and did you get coefficients of 2, 3, and 2? With sodium plus iodine, since iodine's diatomic, its correct formula when it's an element is I2. All right, so there we go. 2, 1, 2. Hydrogen plus oxygen produces water, right? Both are diatomic elements, so it's H2 plus O2. All right, and then forming 2 water molecules. And then finally, this is the one a lot of people missed. Aluminum plus oxygen forms aluminum oxide. So we never bring things across. We have to refigure out the formula when it gets to the other side of the area based on its charges. Oxygen -2, aluminum +3. All right. Then we got to these pesky decomp ones that weren't hard, but they're odd. So yesterday, we were talking about the fact that how would you even know what they decompose into? And the answer is you wouldn't know. That's why I gave you the products. Each time I gave you the products. All right, so most of these had coefficients of 1 because they broke apart so nicely. All right, we looked at these a little bit yesterday. All right, and then here's the one that was bothering people so much. Subscripts do not cross the arrow. You have to rebuild the formulas on the other side. All right, finally, we got to, don't pack up until we get to the end of this so you get to see everything. So here's the ones you had not seen balanced, all right? So butane plus oxygen is 2, 13, 8, and 10. How did you do? 5, pentane, the coefficients are 1, 8, 5, and 6. Hexane, the fuel, combusts. The coefficients are 2, 19, 12, and 14. Monster coefficients, right? Then ethene was 1, 3, 2, and 2. So in all of these, carbon dioxide and water were the products, and it was always a fuel, a hydrocarbon fuel combining with oxygen. 8, the coefficients were 2, 5, 4, 2. And finally, benzene, number 9, 2, 15, 12, and 6. So the content library will have these so you can look up them. And then we actually practiced on photosynthesis. All right, now the idea of the unique details, a fuel is usually a hydrocarbon, it's called, with carbon and hydrogen in it. A fuel sucks the oxygen out of the air. The reaction proceeds till the fuel is gone, And the products of complete combustion are CO2 and H2O. So remember to put out a fire. Don't you either have to put a lid on the pan to keep the air out, or you have to remove all the combustible materials, which is what they do in forest fires. You know how they burn everything ahead of a fire? To get rid of what's combustible to slow down the fire. So typical hydrocarbon fuels are methane, propane, and butane, as well as gasoline. All right, and then we talked about photosynthesis and why that was important. All right, now we had practice identifying these yesterday. All right, so you will be able to go through and see the coefficients and the kind of reaction for every one that we did. All right, so we are done. All right, I wish you the best. Study any part of this that you feel is very unfamiliar.